Okay, so good afternoon. This lecture will continue what we have been saying about equality constraints. So this picture represents a simplified situation of a function of two variables, x1 and x2. And the blue lines represent the level curves, that is to say, the local place of x1 and x2, of the points x1, x2, for which the function is constant as a given value of constant. We have seen this slide already, but let's go a little bit through it. And I want to minimize this function with respect to x1 and x2. But I have a constraint, and my constraint is represented by this line in red, which is satisfies the equation h of x equal to 0. So your minimum is should be found over this red line, and it can be shown. It can be shown that the constraint minimum for differentiable functions will appear in when the constraint is tangent to the level curves at this point Q. So we have an unconstrained minimum P, but we have a constrained minimum Q, which is over the red line, and it is where the red line is tangent to the level curves. Yes? Any question? Okay. Now, we can have inequality constraints as well. So this means that there are regions of the space x1, x2 that are allowed for the minimum to exist. And I've depicted here, again, two situations, very simple situations. In predictive control, usually we have much more variables. So here we are just considering optimization with respect to two variables, so that we can have a graphical idea of the situation. And on the left, the allowed region contains the minimum of the function, the unconstrained minimum of the function. So in this case, the constrained minimum is just equal to the unconstrained minimum. And on the right, the allowed region is this white part below. So it does exclude the constraint minimum P. And so in this case, we say that the constraint is active. In case A, the constraint is not active. In the case B, the constraint is active, and the constraint minimum will be in Q. Okay, these are just some very simple heuristic remarks, and we would like to have some tools to systematically deal with characterizing the optimal points in the presence of constraints. So first we have a technical condition, and we suppose that you have not one but several constraints. I will consider first equality constraints and later inequality constraints. So suppose that you have n equality constraints that are defined by these functions h. So h1 of x is equal to 0, h2 of x is equal to 0, and so on. Okay? And we want to study the minimum of f over the set defined by these equality constraints. We are assuming we are assuming that the gradients of these functions hi that define the equality constraints are linearly independent at the optimal point. So this is a condition to prevent some degenerate cases for which what I'm going to say next will not apply. In general, this is readily verified. This condition is readily verified. So to tackle with the constraints, we use what is called dual optimization. So we have a dual primal problem, which consists of minimizing the function f of x. F is a function between Rn and R, which I'm assuming it is differentiable, and it's defined inside some domain D. And I want to minimize f of x, but subject to these constraints hi of x equal to 0. There is an equality to 0 missing here in the slide. I forgot to correct it. So we replace this problem by the problem of minimizing the so-called Lagrangian function, where the Lagrangian function is a function of x, our primal variable, but also of the so-called Lagrange multiplier vector. So lambda is a vector with that has a dimension equal to the number of constraints. And the Lagrangian function is f of x plus a linear combination of the constraint functions hi, and the coefficients of the Lagrange of this linear combination are the Lagrange multipliers lambda I. Okay, so we built this, and then the conditions for optimality, they are the so-called Karush-Kuhn-Tukey conditions, or KKT. They are written in this way. So the gradient of the Lagrangian with respect to x is 0, and the gradient of the Lagrangian with respect to lambda is also 0. Now, observe that what is the gradient of the Lagrangian with respect to lambda? You should compute the partial derivatives of L with respect to lambda 1 and lambda 2 and lambda 3. So basically, when you compute this vector, remember that this is a vector, what happens is that you are not getting nothing more than, okay, f of x does not depend explicitly on lambda, so the partial derivative is 0. And here, the partial derivative with respect to L lambda I is just hi. So when you equate the gradient of L with respect to the vector lambda, what you get is the vectors h1 of x, h2 of x, and so on. So it's nothing more than the constraints. Okay? So the second part. The first part is given by this expression, and we are computing the gradient. This nabla also is another symbol for the gradient with respect to x, and you equate this to 0, and you get the optimal point satisfies this vector equality. Now, how can we use this to compute the optimum? We use this expression. In Portuguese, we have an expression which is healing the dog with the feather from the dog. Curar o cão com o pelo do cão. Okay, so this is a little bit like that popular saying. First, we compute this condition. Okay? So the gradient of L with respect to x, and equate this to 0. Now, L, remember, depends on the terms lambda. So this gives us a relationship between x and lambda. And we can express our primal variables x with respect to which we are optimizing in terms of the Lagrange multipliers lambda. Now, on the second step, we consider the constraints h of x equal to 0. And we are going to replace here x by its expressions in terms of lambda that we have obtained in step 1. So in step 2, we end up with an equation which is nothing more than h of x, but x is expressed in terms of the lambdas of lambda. So we are going to have an expression which is a function of the lambdas equal to 0. And on step 3, we solve this equation, and we get the Lagrange multipliers lambda. Then we go back to the first. I'm sorry. We go back to the first step where we have expressed x in terms of lambda. Now we know the lambdas, so we replace the values for lambdas, and we get the optimal values for x. Let's see one example. Please bear in mind that you can interrupt me. When you don't understand something, just let me know. Let's see one example about this. So, suppose that my function is x1 plus 1. Well, this is a function of two variables, x1 and x2. And x1 plus 1, this is nothing more than a plane. No, this is a plane. And then we have a constraint, just one constraint. So we only have one function x, h, which is x1 squared plus x2 squared minus 1 equal to 0. This means that x1 and x2, they are over a circumference. Okay, so a circle. So the optimization is bound. Okay, so you should travel in this circumference and find the minimum value of x1 plus 1. Okay, now what should we do? We should write the Lagrangian function, write the Karush-Kuhn-Tucker conditions, which is nothing more than computing the gradients, find the stationary points of the Lagrangian function, and then we have the result, and finally, I would like to have a solution. I will give you a couple of minutes so that you can try to solve this problem on your own. Of course, if you go to the slides, the solution is there, but probably if you have a couple of minutes, you will have this. So take note of this, because I will place the previous slide. Right, the function is x1 plus 1, that's our f, and our h is x1 squared plus x2 squared minus 1 equal to 0. Okay, so try to follow this algorithm, let's say. You will have 2 minutes. After that, I will show the solution myself. If you want to ask me something, you can. Make an effort. So in this case, lambda is just one, as just one component, because we just have one h. So start by writing L. And L, remember, L is f of x plus lambda h. In this case, which this summation is just for one term. Okay, so L is the function x1 plus 1 plus the Lagrange multiplier times the constraint x1 squared plus x2 squared minus 1. And we compute the gradient of L with respect to x. That is to say, dl dx1 and dl dx2. Well, dl dx1, this is just 1, plus this is 0, and then we have 2 lambda x1, and the other terms do not depend explicitly on x1, so the gradient is 0. Okay, so dl dx1 is just 1 plus 2 lambda x1, and I equate this to 0. And I have a relationship between x and lambda. Now, I do the same for x2. dl dx2 is nothing more than, well, these first terms x1 and 1 do not depend on x2. The first term, lambda x1 squared, does not either depend on x2. Then we have x2 squared, which is the derivative with respect to x2 is 2 lambda, don't forget the lambda, x2, and then the derivative of 1 is 0. And of course, we have the constraint. And from these first two equations, we can express x1 and x2 in terms of lambda. And if we solve, the solution is very simple. So x1 is minus 1 divided by 2 lambda, and x2 equal to 0. Now, we plug this into the sorry. We'll plug this into our constraint. So x2 is 0. Okay, this term gives you 0, and this term is minus 1 divided by 2 lambda. And what I get is an equation, which is written here, that can be solved with respect to lambda. Now, we have 2 possible lambdas, but only one is the good one. And let's assume it's the 1/2. Later we will discuss this. If lambda is 1/2, then I go back to the expression of x1, and I replace lambda by 1/2. So this gives me x1 equals to minus 1 divided by 2 times 1/2. That's minus 1. So the optimal point is x1 equal to minus 1 and x2 equal to 0. Can someone tell me, if I considered lambda equals to minus 1/2, what would have happened? Can one of you explain this paradox that we have 2 points? Do we have 2 minimum? Or How could I decide what is the good lambda? No volunteers?
We would have found the maximum because it's also a stationary point, and to decide we would have to plug in both lambdas and check which one was the minimum.
We could check. In this case, that's correct. We could check. In this case, look at what happens. We have two stationary points, one here and one there. One corresponds to the minimum and the other corresponds to the maximum. Okay, so in this case, it's very simple to remove the ambiguity here and to understand why do we have an ambiguity. So any question about this example in this method? If not, let's go on. Now let's consider another example, which is a classical example. This is it can be related to MPC, but even if we don't consider it in relation to MPC, it's a classical example, so it's worthwhile looking at it for 1 or 2 minutes. So we have this system of underdeterminate equations, AX equal to B. This means that we have more unknowns than the equations. So what am I going to do? I'm going to solve this problem. I'm going to find the solution that has the smallest Euclidean norm. X transpose X is the square of the Euclidean norm. So I'm going to find the minimum norm. If I find this minimum square norm, that's equivalent to finding the minimum norm. But of X subject to the fact that X verifies AX minus B. So I have one constraint, which is AX minus B, and I want to minimize X transpose X. So what shall I do? I will write the Lagrangian function, which is the function that I want to minimize, X transpose X, plus lambda transpose AX minus B. That's my H. And now I compute the gradient of L. Remember the rules. So when I have X transposed AX, the gradient is 2 X transposed A. Now my A is just the identity, so the gradient of X transposed X is nothing more than 2 X transposed. Plus, then I have one vector internal product to X, so this is a linear term. And the gradient is just lambda transposed A. And then the gradient of lambda transposed B is just 0 because it does not depend on X. Now, I can transpose, I equate the gradient of the Lagrangian with respect to 0, and I transpose because not to work with X transpose, but with X. So the transpose of the transpose is just X, and here the transpose of lambda transposed A is A transpose lambda transpose, which is lambda. Okay. And from here, I can solve the equation for X and express X in terms of lambda. Now, if I compute the gradient of the Lagrangian with respect to lambda, that is nothing more than the constraint. So I start from here, AX minus B equal to 0. And what I do is I pick up the X as a function of lambda, and I plug it in the constraint. And I got this equation that I can solve with respect to lambda. And then, having obtained this expression for lambda, I go to the original condition X equal to function of lambda, and I use this expression. And I finally get the answer, which, well, don't forget that a scalar can be moved in this product. So this -2 will cancel this -1 out. So that's the final answer. Any question? Okay, so we have one we have one tool to solve equality constraints based on Lagrangian multipliers. Now, let's consider inequality constraints. So my problem, of course, I can consider mixed equality and inequality constraints. In a moment, I will tell you how to mix both things. So our problem is to minimize with respect to x this function f of x, subject to a number of constraints. Suppose that we have m constraints, gix smaller or equal to 0. And these inequality constraints, they correspond to some shaded areas. And we have here two situations. The boundary, observe first that the boundary of these shadowed areas is given by gi of x equal to 0. And I have several of these gi. I just represented one. Think or consider that I could have so many of these constraints that they do not intersect. Then I say that the problem is not feasible. O problema não é viável, não tem uma solução, não há nenhum x que satisfaça todas as restrições. So we have these two situations on the left and on the right. On the left, the minimum, the unconstrained minimum of the function f is inside the region defined by the constraints, but on the right, I have a situation in which the unconstrained minimum is outside the region defined by the constraints, the allowed region. So the shadowed here means allowed region. So I will have to find out this point, which x star, which is the constraint minimum. Now, what are the conditions now? Again, you form a Lagrangian function, which is again our primal function that we want to optimize, plus a linear combination of the constraints that can be nonlinear. And I also call this mu I Lagrange multipliers. Now, the complementary conditions are given by these conditions, mu I gi of x is equal to 0. Now, how can we give an interpretation for this? Suppose that we are in the situation on the left. So in the situation on the left, the constraint and then constraint minimum are the same. This means that the mu I should be 0. Okay? And we are enforcing this condition for mu I equal to 0. Lambda, or the Lagrangian function, is nothing more than our f, and the minimum of the Lagrangian is nothing more than the minimum of f, the unconstrained minimum of f. Now, suppose that we are on the situation on the right, and now the minimum will occur at the boundary of the constraint. So in this boundary, gi of x will be 0. And then mu I will be different from 0. It will be free, or at least free from equating the constraint. And gi is 0 and mu I will be different from 0. Okay? What happens? What happens is that the mu I, I'm not proving the method, just giving you some hints, some intuition. mu I will be such that this function will now have a minimum at x star, the constraint minimum. Okay, so this summation of the constraints will be such that they modify the original function, such that now the minimum with respect to x of the Lagrangian will be at this x star. That's the technique. The proof is rather involved, it will not be given. How can we find this optimal gradient? One possibility is to give is to find the Lagrange multiplier using a maximization algorithm, and from that it is possible to see that this gradient can work. It's nothing more than a gradient scheme that tries to do a maximization. So you see that when g is 0, g of x is 0, okay, what happens? If this is 0, this term is no longer there, and mu of k plus 1 is equal to mu k. So k here is the index of the number of iterates. We are iterating. So at least the equilibrium point is correct, or at least it has an equilibrium point, better to say. Now, how can I this gamma of k, it will be it's a gain of progressing in the direction of the gradient. We can interpret mu kg as a gradient. It's not obvious here, but you can believe me. And this gamma should not be selected as you wish. For instance, one would say, well, let's use a constant gamma very small, 0.001, something like that. Well, it will not converge. For this algorithm to converge, the gamma must go to 0, because otherwise we are always receiving a correction from this term. But furthermore, there should be a balance. The gamma should go to 0, but the sum of the series of the gamma should be infinite. And the sum of the squares of the gamma should be finite. So basically, the first term tells you that you should be able to move from the initial value of mu, where you are, and attain the correct value. And that's the reason why we have this term here, this condition here, that the summations of the gamma is infinite. But the sum of the squares should be finite. In practice, what you do, you select something like a constant divided by k. Okay, that verifies these two conditions. Actually, it will be very improbable that in your life you use this algorithm. Okay, any question? Although it appears, for instance, in reinforcement learning, you will find exactly the same conditions. That's why I'm mentioning this. Let me give you one example. Well, this escapes a little bit, or goes a little bit further than the course that we are studying. But let's spend a couple of minutes here. So I have, this is a second order plant, linear, it's linear. I haven't written even the equations, but it's a linear plant, it's second order, but I'm controlling this plant assuming that it is first order. So I have two gains, and one of the gains multiplies the output, and the other multiplies the input of the plant. So I'm using a state which is made of the output and of samples of the input, okay? Like in a computer control setting. And so what happens? What happens is that there are values for F1 and F2. You see F1 in this plot. You see the resulting cost, and there are values for which the closed loop becomes unstable. But there are other values for which it becomes stable. Actually, this thick line here is the stability boundary. How can we compute that? Well, that's a long story that I'm not going to tell. And inside this stability region, I have several values for the cost, and my cost is nothing more than the variance, so the expected value of the square of the output. Okay, so in stationary regime, that means that you turn on your controller and you let your plant evolve, and you do a lot. You observe the Y. If it is stable, this Y will, you pick a number of samples, for instance, if you want to do it in a practical way, and you square the samples, you sum all of them and divide by the number of samples. So that's the meaning of this expectation here. Actually, we do this analytically. There are ways of doing this in a very efficient way, but the idea is this, okay? So different values of the controller gains yield different values for the variance of the output. Okay, the plant is affected by stochastic disturbances like wind or something. And one thing that I can ask is, what is the value of F1 and F2 that minimizes the variance? Okay, that's that square over there, that cross over there. Okay, so it's 1.70 something and minus 0.25 or 0.3 or something like that. Okay, that's this square here, this cross here. Okay, now I solve another problem, and my problem is I want to find the minimum of the variance of the output, subject to the fact that the variance of my manipulated variable is smaller than some c squared. Okay, so c is a number that I say in this case 1.88 in this case. Okay, so I can compute. Remember, u is depends on, it's a feedback controller, so u depends on y. Y is affected by noise, so u will also be affected by noise. Okay, and actually I can compute here the boundary of the allowed regions for the control values, and the control values are imposed by F1 and F2. So this corresponds to the optimal allowed regions for F1 and F2 given this constraint. Now, write a Lagrangian function. The Lagrangian function is the expectation of the y squared, so the variance of the output, plus some Lagrange multiplier mu times the expectation of u squared minus c squared. Okay, so I've omitted the term mu c squared because this is a constant. Once I fix the Lagrange multiplier, this constant will not affect the Lagrangian function. Okay, so what is this? Oh, it's something that you are probably familiar with. It's a quadratic cost on the, you are weighting the output, the deviations of the output, plus, and then you have a Lagrange multiplier that weight acts as a weight with respect to the power of the input. Okay, that's our good old quadratic cost. Now, it's a stochastic. It's stochastic, but apart from that, it's the quadratic cost that we have considered in the very beginning of the course. And it is interesting because the weight on the control variable is nothing more than Lagrange multiplier. So perhaps this example, it's a little bit fuzzy, but it's telling us something which is quite interesting. And this is that the weight of the manipulated variable, of the control variable, in a quadratic cost can be seen as a Lagrange multiplier, and we are implicitly doing imposing a constraint on the value of the control. Okay, so we can think of that as something we are imposing a constraint. Of course, we can write the condition of the Lagrange multiplier. Remember, it is the Lagrange multiplier times the constraint. That's our G. Okay, is nothing more than the variance of u minus c squared. This is nothing more than my constraint function G, and this product should be 0. And I can adjust the mu such that using the Robbins-Monroe gradient algorithm, that will give this. Now, I have one problem, which is I don't know what is the expectation of u squared. So I just replace it by its instantaneous value. And then when I do a lot of these computations, I hope that this will converge to the expectation of the u squared, to the variance, and actually it does. So one algorithm might be solve a control problem that minimizes a quadratic function, and then in each step go on, and instead of having a constant weight on the manipulated variable, you adjust it with this. Okay, and you will converge, you see, to the constraint minimum is there. That's the small bullet there, and the algorithm that I was using, which was a preview control algorithm, goes there to quite near after some iterations. Okay, so what would I like you to retain from here? That the weight on the control function in a cost function can be seen also as a Lagrange multiplier. It is as we are implicitly forcing a constraint. Any question? Okay. Now, in practice, you need a numerical solver. And numerical solver algorithm is something which is very, very difficult. I mean, usually you will have to rely on software developed by others. And you know from the laboratory that we have solvers in MATLAB, one for unconstrained problems, that's fminunc, and others for constrained problems, that's fmincon. And even there, you can decide between families of numerical algorithms without making, well, this is actually a very complicated issue, and I'm not even an adequate person to speak more about it. But let me tell you what is my experience. in a practical way. There are two families of methods, that's interior point methods and sequential quadratic methods. Okay? Interior point methods come from the fact that you can solve, if you have a convex problem, then you can reduce it to a linear programming method. So you approximate your problem by a sequence of convex problems. And you solve these linear programming methods. When you solve a linear programming method, you have a linear function, and you have linear constraints. But these linear constraints, they define a region. And you can you can show that your optimum will be somewhere in this boundary defined by these constraints. And you can try to find it in either of the ways. You can go through the boundary and try to find what is the best point, or you can go through the interior of the region defined by the boundary. And that's why we have this expression interior point methods. And there are also sequential quadratic methods, which is a different family, in which you solve a sequence of quadratic problems with the linearization of your constraints and your function. The function is approximated by a quadratic function, and you approximate the constraints by linear constraints. My experience, you can select both in FMINCON. My experience is that for MPC problems, SQP work better, although this is not a definite decision. Maybe you can find some problem in which interior points are better, but up to now, my experience was that start always with SQP. So the FMINCON solver solves this problem, this family of problems. So you want to minimize with respect to x some f of x, and then you have the first line, you have nonlinear constraints, inequality constraints. And you can also have nonlinear equality constraints. That's the second line. Okay, so these are functions that you can program when you call FMINCON. Then you can have also linear inequality constraints and linear equality constraints. You have, for that, you have to find out these matrices A and B, A and B. And you can also impose, this could be programmed as a special case of linear equality constraints, but you can also directly impose minimum and maximum values for the x variable. So FMINCON, basically, you have to define a function, the name of a MATLAB function in which you program the computation of f, initial value, then this a, b, a, q, c, q, x lower bound and x upper bound for the constraints, and also the options allow you to select the solver. And this P1, P2, etc., they are parameters that you can use to update this nonlinear function C and C. Okay, so this is a rather shallow presentation of FMINCON. If you ever want to use it, you will have to go to MATLAB documentation set and see how it does, but that's the idea. Okay, so I will not make a break here because I will not be using the 2 hours. let me show you a couple of slides and then one example about model predictive control, in general, nonlinear model predictive control. Now we know the idea, but there is one thing that I would like to call your attention. Once we are equipped with this fact that we can impose constraints. So we are at time t, that's the present time, and we have some horizon of with endpoints. And L is some function, can be a quadratic function. And we can also impose some terminal function of the terminal state. Sorry, my throat is about to end. Now, one possibility might, as we have done before in the previous lecture, is to express the future states in terms of the control, of the future controls. But you can do a different thing. You can think of the states, of the future states, as free variables for the optimization. So you are minimizing not just with respect to the sequence of future controls, but also with the sequence of future values of the state. Okay? If instead of the state you have here y, you can also do it. And then you have to impose a constraint, which is the dynamics. So actually, this is not just one constraint, but it's a sequence of constraints that apply for all the future times between I equal to 0 and I equal to n minus 1. So the novelty here is that you are optimizing with respect to x, but then you impose your future values, that the future values of x are related to the use with constraints. So you instead of imposing a priori, you let the algorithm do the computations. And of course, you can impose constraints on the state or on the state variables. But the novelty is here. And this simplifies programming a lot. The other thing I would like to mention is we have solved the problem in the previous slides, the problem in which you want to drive the output of the plant to 0. You can also build, this is no longer the predictive models, okay? Because this is actually nothing more. This A and B are the matrices of the state model, okay? But then I build this enlarged matrices. I call it A tilde, B tilde, and so on. Okay, there is an E here that is related to the state. And this allows you to work with future states and not, remember that this vector is not n components. It's much more because it's the dimension of the state times n. Okay? But using this notation, you can write, if you have a quadratic cost, you can write it in this way, again, subject to this set of predictive models. Okay? So if you have a problem with in which you want to control the state and not just the output, you can do it like this. Any question? I would like now to show you some examples of these. Examples have been done by a student of mine in a master thesis, but I think it's quite interesting. So let me sorry. Okay. Okay, so can you see this slide now? Vehicle dynamics, a tricycle model. Can you see it?
Yes.
Thank you. So this this presentation is borrowed by a former student of mine called Christian Sava. And I think it's interesting. So in this case, we have a tricycle model. So a tricycle model, in a tricycle model, you can, the dynamics are written here. Okay, so your manipulated variables are the velocity and the angle, this angle theta and the velocity. So this velocity is something that you can make fastest or smallest, and the theta, the angle, you assume that you can change it. So they are two manipulated variables, and this vehicle is moving in a two-dimensional plane with coordinates x and y. So x is not the state; it's just the horizontal coordinate, and y is the vertical coordinate. And these are the equations. So it's non-linear, as you see. H is the sampling interval. And the objective, we have several objectives. So one of the first objective is to move from one point to another. So we have a cost function that just says we have a constant point over there. It's very simple. Now, this vehicle is it has some, it's non-holonomic, that is to say you can instantaneously change the state. So if you start with a different orientation, it should go there, and actually goes. Now, let's see what happens when how the prediction horizon affects, and we have a constraint. Okay, this constraint comes from the fact that we have a column, that red circle over there. Okay, so this is a relatively smaller horizon, h equal to 10, and he sees the object only when it is close to it, but then he tries to avoid it. Now, let's increase it, and he sees it before, so the horizon enlarged allows you to have a smoother trajectory. Usually in an MPC, when you enlarge your horizon, you get better results. Things tend to be smoother. We can have several obstacles, and this means that it is solving these obstacles. How are they considered? They are considered by having constraints in actually non-linear constraints in the MPC problem. Now, don't ask me why. Don't ask me why, when the horizon increases, that it avoids and it prefers to go around the obstacle of the forest. And that's just a solution. I don't have a solution, easy interpretation for this. Now, we can also have obstacles that move. So here is a little bit myopic, so it has to go back. These simulations take a lot of time. So these are movies. I'm not running the simulation in real time. So let's see what happens when we increase h. When we increase h, he sees it in the distance, so he deviates. Does not have to do that maneuver. So you can also have several vehicles and impose a constraint of the distance between both vehicles, such as to simulate a situation in which they are carrying some object, one in one side and the other in the other side. Now we have to tilt, but then it takes a long time to return again. So here we can change the cost function to penalize deviations with respect to the line. So deviations of the line between both vehicles with respect to the line that connects both targets. So if you impose that deviation, of course, here it has to tilt to pass, but then it's much faster in getting the right orientation. So this illustrates the situation in which you have to change your manipulated variables, your cost functions. Now, this is a situation in which there is a river, so they approach a river. Now you can't see what happens, but basically they do some maneuvers to cross the river. Now, this is a situation in which you have different coefficients of viscosity before the river and after the river. Okay, suppose below, suppose that you have sand and water, and you want to go from one point in the shore to another point in the sea, and of course you will probably walk more in the shore than you swim in the sea. Okay. And this is the decision is automatic. Okay, now you can have obstacles and so on. That's a combination of course, when you go on doing these examples, the computational load greatly increases. Okay, any question? So I will stop here. I will not go through the 2 hours. Is there any final question that you want to ask? If not, thank you.